Dr. Daniels is going to talk about some of our upcoming inevitabilities, perhaps, and then we're going to go to a break, and then we come back. We're going to put to you an effort to work out at a small table about trying to be a long-range planner for within a drought condition. So with that, I'm pleased to hand it over to Dr. Daniels.
Actually, I'm not with UC Santa Cruz. That's where I got my PhD from, but just so you know. He mentioned I was going to give a sobering talk. Actually, I'm going to give a very scary, freaky talk. I've thought about giving this, on Halloween night, and that would probably be appropriate because it is quite scary, but the future is a little scary. One of the things is that some people who really know these things have said that the biggest impact of climate change on us humans won't be temperature. I mean, it will get warmer, but the biggest impact of us will be water. Because all over the world, water is in short supply, sometimes critically, and this is going to really impact that big time. First of all, thanks for Eric for his talk, where he was talking about the Oroville Reservoir and shared water with him in Sacramento, and I want to unfortunately say he's wrong. We are one of 2 counties in the state that neither imports nor exports water. So we have to make do with what we have. So if you want to see our water, there it is right out front. Right out the window, you can see our water, and that's our only water. So we can't expect the cavalry to come over the hill and save us. It's just not going to happen. So we have to make do with what we got. Okay, before we talk about how climate change impacts water, let's talk a bit about water. So this is the water cycle, as you probably all know. So the water supplies we have evaporate up into the sky, they condense, form clouds, precipitation comes down. Some of that infiltrates into the ground, some of it doesn't, it runs off and goes into streams. And the stuff that infiltrates, some of it's picked up by roots of trees and so forth, and the stuff that gets through all that actually recharges then the groundwater, which is down below. So you can see there's weather, climate is the top part, middle part surface water, and the bottom part is groundwater. So, recharge is not constant. So what we got 20 years ago is not what we're getting now and not what we're going to get 20 years from now. And because climate is changing, which means precipitation is changing, which means recharge is changing. So it's a scary world we're in. Nothing's constant other than change. Okay, recharge is not directly connected to precipitation. Some hydrogeologists kind of think that okay, we take 20% of the rain we get and that's recharge. And that's not the way to do it because it's a very complex partitioning that takes place between precipitation we get and how that ends up as recharge. There's a little bit of what it's like. So in the upper left-hand corner, you see precipitation. Then you see next the water on the surface and all these parts and pieces and everything flowing around. Let me point you to the interception thing. That's what we're going to talk about next. Oh, by the way, precipitation is not constant. Each of those little boxes you see is dependent on temperature or radiation or wind, humidity, plant types and how they cover the surface, animals, soil profiles, timing, et cetera, and all of those are climate dependent. So this whole big picture you saw there changes a little bit all the time. Okay, that box there, interception, what is it? It's very important. Do you even know what it is and why it's important? Interception is the rain that's caught by plants, leaves, bushes, even grass, and then evaporates without ever reaching the ground. And why is that important? We lose almost 17% of our precipitation to interception. It never hits the ground, it just goes away. That's amazing. A lot of people think, oh, we got so much rain that, well, we have a lot to make use of. And we lose 17% right there off the top before it even touches. If you've ever walked under a tree in a rainstorm and noticed, that underneath there is all dry and things, and you thought, well, it just hasn't made it through yet. Nope, it's not going to make it through because it's already landed on the leaves and started evaporating. How much of that precipitation is recharge? I'm going to talk a lot about my basin, which is the Mid-County Basin, so it's Aptos, Soquel, La Selva, that area. The Mid-County Basin, it's 9.8%. So less than 10% of the precipitation we get ends up in recharge. And some of that recharge actually isn't supply. It goes to the streams with what's called base flow. So about half of that gets into the recharge, into groundwater, ends up keeping our streams alive in the summer and fall. That's the only thing that keeps streams alive in summer and fall, is that base flow. So we actually have very little water to make use of that comes down. And these are all the various fractions. You don't look at all the pieces, but the important thing is if you add all those up, all those things, the total evaporation and transpiration, as it's called, is about 2/3. So of the rain we get, 2/3 goes up in smoke, if you will. Is this recharge to precipitation relationship linear? So if you get 10% more precipitation, do you get 10% more recharge? That's not the case. The relationship is curved, with the larger storms producing the largest recharge. And there's an example of how it's curved. That's for our mid-county basin. So you see, as you get a bigger storm, the amount of recharge goes up, not linearly, but more than linearly. And the most critical thing is look at that thing down at the bottom there. We get about 30, 32 inches of precipitation in the mid-county basin. And if you get down to around 20 inches, so 2/3, you get essentially zero recharge. So when you talk about, a 20 or 30% less precipitation that we got this year than last year, you need to look at, you may be getting zero recharge out of that, which means, the streams that keep the riparian habitat and all the fish and everything alive, and then a lot of water users. A lot of water users are surface water users and groundwater users. That's pretty tough. Is recharge just dependent on the annual precipitation amount? No, it also depends on seasonal precipitation, which is changing. So here's a couple of quotes. There's going to be less precipitation in the fall, November and December, and the spring, March and April. And you can see a little graph there of what used to be and what's going to be. The critical thing is we're going to go from a rain season, which is currently about 4 months long. Our big rain months are December, January, February, and March. And we're going to lose 2 of those months. So we'll get all of our rain. It may be the same amount, but we'll get it in 2 months instead of 4 months. So it's going to be January and February. That means the storms will be bigger. So flooding becomes an issue. Bigger storm means probably not as much of it will soak into the ground, so more of it will run off. So we won't have less supply. And it also means that our dry season, which is currently 6 months long, so we need to have water to get us through that 6 months, will go to 8 months. So keeping us with water for another 2 months is going to be yet that much more difficult. These are backed up by 2 scientific papers. Does recharge just depend on annual and seasonal precipitation? No, it also depends on daily timing and patterns, some of which are not well understood or appreciated. So for example, if you look at precipitation events, and we've got an event going on right now, the intensity of those events on how much rain we get per day during those events is getting weaker, about 3% weaker per decade over the last 120 years. The duration of the storms, however, is getting longer. So if it gets 3% weaker, but it lasts over 2% longer, then as you might think, you're getting about the same amount of water, but it's a different timing. And also the timing between events is also changing. So the downtime, the dry time between rain events is increasing by about 2%. So you might say, okay, well, who cares? But there's an important point to this. If you take these things and put them into a hydrology model to see what effect they have, so you take those trends and you continue them for another 30 years, and you apply those trends to the mid-county basin with exactly the same precipitation as we got in the last 30 years, but just the timing changed. Evaporation increases by almost 4.5%. Recharge goes down by almost 7%. Base flow, which is again the thing that keeps fish alive in the summer, goes down by 6%. And total stream flow goes down by 3%. Those are big impacts. That's without anything, that's getting normal precipitation. But just these almost hidden timing changes is causing us to lose more. Spooky, isn't it? Something you never realized was even happening is impacting your water supply. Recharge also depends on the temperature, amazingly enough. So here we go. Simple physics says every time the the temperature goes up 1 degree Fahrenheit, evaporation increases by 4%. And so you can see here there's a graph of how much the temperature is supposed to change by two different climate models, the red one and the yellow one. And that increases by about 10% from where we are today. So from 70 degrees up to like 77%. And you see the evaporation increasing by 30% between now and the end of the century. So let's look at a little scenario. This is the Mid-County Basin. We get about 32 inches of rain, and our temperature is about 70 degrees, as I mentioned. Evaporation, transpiration, as I mentioned, causes us to lose 21 inches of that 32 inches of rain we get. That means 66% of the rain we get evaporates. So we are left with 34% of the rain to do everything we need to do. Domestic use, commerce, business, agriculture if we had any in our area, stream flow and fish, and in our basin we need to keep seawater intrusion out. So some of it has to go out into the ocean to keep pushing that seawater intrusion back out again. So what's the future going to hold? Okay, temperature will go up 10% from 70 to 77 degrees. Evaporation therefore increases by that 30% I showed you. So instead of losing 21 inches, we're going to lose almost 28 inches. That means 85% of the precipitation will be lost, and we have to make do with 15%. That's critically important. This means instead of 34% of the rainfall being available for what we want and enjoy in our lives, we'll go down to less than 15%. So we will lose half of our available supply just from this temperature change. Notice what this means, that if you had a normal rainfall year, but much higher temperatures, you could have a drought. A drought with normal precipitation. And think if it was actually a drought year. Scary stuff. But that's the future. The biggest impact on us isn't changes in precipitation amounts. It's some of these timing things I showed, and particularly temperature. And that's not theoretical either. The 2015 drought was the warmest winter we've seen in the historical record. So that one with the red arrow pointing at it. And you can see it was a lot warmer than any winter we've ever had before. Even the year before broke the record. But this last 2015 year broke it even more. And so what did that do? As you can see down at the bottom there, 8 to 27% of the observed drought anomaly in 2012 to 2014 was caused by that temperature spike. So that drought was caused not by just having less rain, which we did have, but losing more of the rain that we did get to the temperature evaporation. So about 15% of that drought was caused by the warm temperature. A lot of folks don't even realize that, but it's the case. Again, another scientific paper. There are some other changes that are predicted. The average precipitation here is predicted by some climate models to increase a small amount, very small amount, I think, 1% maybe. And there's a lot of uncertainty about that. Whereas climate models do a really good job of estimating temperature, and they all pretty much kind of agree. There's a little spread. The estimates by climate models for precipitation is very wide, with some of them predicting much, much more rain, and some of them predicting a lot less rain. And the average is about 0. So if you looked at the climate models, you might think, okay, well, if the average is 0, we're all set and everything's good. That's going to be about the same. But that's just the total amount. The other factor is that the variability increases substantially. So the dry years will get much drier. The wet years will get much, much wetter. In fact, some of these climate model papers have written that we might get wetter up to 35%. So floods, yeah, we're going to get more floods. More damage from these floods, yep, we'll get more of those. So will our infrastructure be able to handle all this kind of stuff? It'll be challenging. And just like this drought we went through, 2015 was the worst drought year in 1,200 years. That goes all the way back to what's called the medieval warm period. Warm period. And of course, what we're going into is the warm period for us too. So the fact that these droughts happen in warm periods is not accidental. But anyway, back then, That's the time when the Anasazi Indians and the Mesa Verde Indians, Native Americans, if you will, they abandoned their homes. And probably a lot of them perished because it wasn't just their home that was drought stricken. It was much of the Southwest. In fact, here's a study I find the most, in particular this one diagram, the most scary thing. So this is, again, another scientific paper. There were 3 climate scientists who wrote the paper. It was reviewed by a bunch of other climate scientists and then published in a journal. So it got a lot of review. And they were looking at what is the hydroclimate going to be like in the Southwest. Over on the left-hand side there, you see those black bars. That is the medieval warm period, 1,200 years ago or so. And you see that most of the time it was under that dotted line, which means most of the time they were in drought for that century and a half. And in fact, some of the droughts were known to be quite long. In fact, you see that first quote up there. For us, there's greater than an 80% chance of a multi-decadal, so at least 20-year drought during the last half of the century. We've never seen anything like that. For us, the biggest drought we've ever seen is about 6 years, and it was a mild drought. As you see from the second quote, we're not expecting mild droughts. We're expecting mega droughts, very intense droughts. And that's shown by this diagram here. Let me go through this with you. So this wiggly line, this brown wiggly line you see going across there, that was derived from scientists who study tree rings. From tree rings, you can figure out what the temperature and precipitation was like when those trees were growing. And so you've seen studies with those kinds of things going back, in this case, over 1,000 years. And so we kind of know what things have been like in the past. That's when, the Anastasies were done in. And over on the very far right-hand side, you see a number of predictions. The blue is, what is the soil going to be like 6.5 feet down? So that's the soil moisture that keeps trees alive from year to year to year. The green is soil down 1 foot. So that's the soil moisture that's used every year for annual plants, so crops and grasses and things like that. And you see that black arrow going down, that's where we are right now. So you can see that we've already seen some going down. In fact, since 2000, year 2000, in the last 18, 19 years, 70% of those years have been dry years. And over the previous century, the 20th century, about 30% were dry years. So already we've seen some change from, up and down to more down and more down and more down. But you can see here, the future is even bleaker. That kind of dotted red line going across the middle there, you can see that's the deepest that any of the tree rings show we've ever gotten in the past. And what they're predicting for the future is twice as intense as that. So, should we be scared? Oh yeah. I don't know, this is why they say that, climate change's impact on water will be the hardest things on us people. And we all need to understand this, this kind of thing, because we can't fix this if we don't understand it and appreciate it and know what it is and how to deal with it. And I like this quote from Lewis and Carroll's Alice in Wonderland. Right? This was the Red Queen who says, "It takes all the running you can do to keep in the same place. If you want to get somewhere else, make things better, you have to run at least twice as fast as that." Which makes sigma a real challenge. How are we going to take our currently unsustainable water supply and make it sustainable when climate itself is getting worse and worse and we're having more and more impacts on just the supply we have today? We're going to really have to work very hard and be very smart about it. And there will have to be sacrifices made. Sustainable water supply planning. Let's talk about that a little bit. I'm on the Mid-County Groundwater MGA, the Mid-County Groundwater Agency, so we're working hard too on these same problems. We all need reliable climate forecasts because unlike, kind of doing something, we need to do the right things. We need to know what the problem is to be able to find what the solution is. Sigma requires that we have 50-year water plans. So we need to know what's going to happen for the next 50 years. So from now till 2070. And reliable is critically important because it's the basis for huge amounts of efforts we're going to put in and very expensive investments we're going to make into solutions. And we need to really understand that those investments and those solutions will actually fix the problem and not just make us feel good that we did something. We also need to consider the forecasting mechanisms. And I can go on till I'm blue in the face talking about these. Unfortunately, climate models don't do a real good job of forecasting. And we in our MGA have done something different. You need to consider what does not work and what does work. And I've mentioned that most of the climate models do a great job with temperature. They can tell you what the temperature is going to be, but a lousy job of telling you what the precipitation is going to be. The 27 or so climate models, something like half of them say it's going to get wetter, and something like half of them say it's going to get drier. And which one you believe? If you can pick one and say, okay, everything's going to be fine, we don't have to do anything, or you can see it's going to get a whole lot worse. The problem is that a lot of them don't look at the temperature effects and the timing effects, and that's really difficult to do. So I want to offer my services. If any of you need any help or want to understand this more, give me a buzz. I went back to school to get this work and understand these things from my own basin, but I'm willing to help your basin too. So anyway, that's it. If you want to take questions now. So is everybody scared now? Did I succeed? Okay, thank you.
So, have a cookie and everything. All right. So folks are going around and getting cards. Let's try to bring some of those cards in quick, specific to Dr. Daniels' presentation. I've been sorting, while Dr. Daniels was speaking, I've been sorting through a number of the other cards that have come in. I'm going to ask the staff, agency staff, to sort of be up here as well, because let me actually do this. Let me do this. Hold on. Well, I need a second to sort of sort through the cards that just came in to make sure if they're specifically for Dr. Daniels. Okay, well, while we're here, Dr. Daniels, you're still there? Okay, all right. What can we do to convince the president and his followers that climate change is real?
Next question.
No, I had one for Eric too. You get one too. So.
Well, you take any subject and there are going to be some people that just don't want to believe. Maybe it's a vested interest. Maybe it's just they believe. They are unwilling to. I even understand there's a flat Earth society. And I don't know whether they really believe the Earth is flat, but they get together and talk about how, the Earth is flat, and maybe a big joke, but there are people that believe all kinds of crazy things, and they just won't. There's some people that think we never landed on the moon, even though we have pictures of the Earth from the moon. And you can never convince them. They just won't believe and they won't listen to facts. I think the biggest thing for me has been presenting the impacts, because these are the things that we, our children, our grandchildren, our great-grandchildren will live in. This will be the first generation that really, really does not get a world as good as the one that we were given. We are going to give them a real bad world, and they're going to have to scurry to fix it.
Okay. With interception, when the water evaporates, doesn't it go back into our water cycle versus being lost, i.e., doesn't it become vapor form that goes into clouds to become rain again? Or does that water vapor move somewhere else geographically in a way that it doesn't help us by the time it falls as rain again?
The average drop of water, most of what we get comes right off the Pacific, drops 7 times as it goes across the United States. And that's the prevailing wind direction because of the way the Earth rotates. So most of the winds go from west to east. So in the east, they get used drops of water. It's evaporation from here, and it goes and lands in the Sierras and produces snow, and then it lands in the Rocky Mountains and produces snow, and then lands in the Kansas and produces wheat, and so it's. I mean, as you see, the evaporation from precipitation that lands on vegetation, and even the leaves have a little holes in them called stoma that they open up to let carbon dioxide in, because as you know, the plants breathe in carbon dioxide and they breathe out oxygen. And when they open up their little stoma, water goes out too. And that's called transpiration. So that's part of the evaporation that happens. And some people have suggested we cut down all the trees. And of course, that's not going to happen, is it? Because that would have other problems, because it means we'd have dry, parched earth in the hills, and that's not survivable. So not much you can do about that.
How do we contact Dr. Daniels?
I think on my first slide I had that, didn't I? That's my website, hydroclimatology.com, and you can send an email to bruce.daniels@hydroclimatology.com. And there's a copy of this kind of presentation on that and several others. So if you want to know more, you can go look at that website.
How do you keep calm and scientific? I don't know if this is a you global or you, but personally, how do you keep calm and scientific in the face of this? How do we collectively address the grief and loss, then roll up our sleeves?
Well, like lots of things, we can sit around and moan and groan and feel bad about things and not do anything, and that doesn't help. So I think all of us need to kind of pull up our boots and do what we can. It's only by doing what we can that we can address this at all. So we can try and do our best. That's all we can do.
Was the Chaco Canyon cultural collapse caused by drought?
Chaco Canyon? Probably. I mean, this was a fairly widespread thing. The medieval warm period was, in fact, caused because it was known in the Mediterranean region. And so, ancient Rome and, they were impacted by it too. It's pretty widespread, but definitely all over the Southwest, it's well known. I mean, they've done these tree ring studies with, trees they found in structures, and they go back, hundreds and hundreds of years. And then there are other kind of things they can look at, the stalactites and stalagmites in caves. You can even see how rainfall was from those. So lots of different ways you can see these things. So it's well known, well studied, and it's widespread.
Regarding climate change, since bigger storms bring more recharge, why does climate change not add more water to the ground?
Well, interesting enough, let's talk about the most outrageous storms you can think of. So let's say we get 36 inches of rain a year, and all of it falls one day a year. So pick your day, but the whole 36 inches drops in one day. Well, you're getting 36 inches of rain. That's more than we get now, so you'd think everything would be okay. But it's only so much of the water can soak into the ground. And the stuff that can't soak in, I mean, it's going through little tiny ground pores. Most of it couldn't soak in, and it will run off, and it would therefore cause massive flooding. And then go to the other extreme, where you get 1/10 of an inch of rain every single day of the year. 1/10 of an inch, 1/10 of an inch. Then the water would come down, some of it would land on the plants and evaporate, some of it would land on the dirt, on the ground, and kind of get the top layer of the ground wet, and that would evaporate too. So you would get almost no recharge. And that's kind of what happens. When you get bigger and bigger storms, I mean, the kind of storms you saw here are kind of the normal ones we've had now. But the big ones are going to get even huger, and for those, much of it will run off. When you get a storm twice as big as we get now, I mean, the streams will just go over their banks, and much of it will then drain away. So, a little bit better is good, a lot better is not good.
Got time for one more question, so we'll go with this. There are 2 different climate change models being used for local SMGWA planning. How do we know which model will best fit this county?
Well, let me just quickly show you what my basin is using. Because I talked about the fact that, here's temperature and it's got a spread, but all of them say it's going to get warmer. And precipitation, all of them are all over the map. So what we have decided to do is, oh, by the way, this is a study that USGS did, the United States Geological Survey, and they were looking at climate models and how they match today. The green areas where they match almost all, and the red areas are where none of them match. Look where California is. California in particular does not fit with any of those climate models, or almost none, most of them none. It just does not work here in California. So what does work? Here's what we've done. Here's our precipitation, and you probably have pretty much the same precipitation. You see some years are wet, some years are dry, and some are in the middle. And what we've done is we've categorized the years by not water, but by temperature. So you can see some of these years here are red, therefore those are warm years. And they kind of match with precipitation, but not completely. And then we prioritize the years based on their temperature, because we know the temperature is going to get warmer. We don't know what precipitation is going to do unless you pick a climate model, and then you're stuck with whatever you picked. So these are categorized by the temperature that these years have seen. And again, we're trying to get warmer years because we know the future is going to be warmer. So there we have it. And with that scenario of taking past years, we know exactly how it rained those years, exactly what the size of the storms were, exactly how many days the storms lasted, all that stuff is known. Then we take those years and string them together, and we use that as a proxy for what the future is going to be. And this was suggested by Dr. Andy Fisher. He's the professor of hydrology at UC Santa Cruz, my thesis advisor. And it was also used by LA. LA uses a model very much like this, where instead of picking one of these climate models for precipitation, they try and pick years out that are going to be warmer.
Okay, well, let's give another hand for Dr. Daniels.